Good morning. Let's get started. Hi, everyone. How's it going? Um, so we will start today talking about cache-oblivious algorithms. If you remember, last time we talked about cache-efficient algorithms, which may have knowledge of the cache line size. At a high level, cache-oblivious algorithms uh, do not have knowledge of the cache parameters like M and B that we talked about last time, but you can still analyze them in the model using the cache parameters, and we'll see how that works. Yeah. Oh, yeah. And please sign up for your groups for the programming assignment if you haven't done it yet. So the sign up will be open until Friday at the end of the day. And if you don't sign up for a group, we'll just randomly assign everyone left over. And you're not stuck with the group that you have in the first assignment. Like if you decide that it didn't work out, you can always change in the next one. So don't worry about it. Okay, great. Okay, so if you remember from last time, we had this ideal cache model. And in the ideal cache model, it models with 2 levels of memory. There's 2 levels of memory hierarchy. Cache size has m bytes, and there's a cache line size of b bytes. So these are the 2 cache parameters, m and b. And we assume this ideal cache is fully associative, and you have an optimal replacement policy, which is obviously not realistic, but we have theory to show that a more realistic replacement policy with more resources can approximate this within a constant factor. So that is why that is an okay assumption to make. And so there's the cache lines are with B, and you have M over B cache lines because you have M bytes, and each line is B bytes, and the memory has unbounded size, and the cache has bounded size. And we are only talking about one processor here, so we're not talking about parallelism for now. And to clarify, like in this model, which is actually how computers work, when memory or when data moves from memory into your cache, like when you access it by your processor, it is never like one element or one word or one byte that moves at a time. It is always at least 64 bytes that moves through the hierarchy. So even if you ask for one, you will get 64 bytes around whatever you asked for. And that is actually how the memory hierarchy works. So, and we are measuring in this model, we have the same measures that we had before. We have the work, which is the regular running time that we have in the RAM model. And then the new measure that we have is the number of cache misses, which is the number of cache lines that need to be transferred between the cache and the memory. And this is always bounded above by the work, but ideally, we would like it to be less than the work. Okay. As a quiz, we talked about the types of cache misses last time. What types of cache misses are not captured by this model for serial programs? Good. Yes, great. Does everybody understand that? Does everybody remember the types of cache misses? Okay, great. Yes, amazing. So conflict misses, because cold misses and capacity misses are captured by fully associative cache, but conflict misses, which are conflicts in the same set, are not. Great, amazing. Yes. Okay, so a very quick recap of where we ended last time. We talked about tiling in matrix multiply. And tiling is this technique where you basically add things in your loop nest. Like normally this is 3 loops in the straight matrix multiply. Instead, we set some parameter s, which is your submatrix size. Now you're doing s by s multiplications. You basically, originally, like in the 3 loop matrix multiply, s is 1. And you just now break it down where s is greater than 1. And if you can know the cache size, you choose your s such that each submatrix just fits in your cache. So s is like root m because the matrices are s by s. And so it takes s squared over b cache misses to bring the submatrices into cache. But once you bring each subproblem into the cache, you don't need to incur any more misses because it is just there. So the analysis is the number of subproblems you have times the cache misses per subproblem that you incur. Number of subproblems is theta n over s quantity cubed because there are n over s side lengths. And yeah, this is the misses per subproblem. And you get this in the end. This is n cubed divided by b quantity b root m. And that is optimal in the theoretical sense. Why is this cubed? Because the original matrix multiply was n cubed, like n cubed work. So the number of subproblems is also n cubed. Does that make sense? Good question. Yeah. questions about this? Of course, yes. So we're trying to analyze the number of cache misses. The way that we're going to do that is we're going to count the number of subproblems that we have times the cache misses per subproblem. And number of subproblems is n over s cubed because like the side lengths are n over s, or sorry, there are n over s of these subproblems in one side, and previously it was like n on one side, and then the work of matrix multiply is n cubed, but now there's n over s because you've cut the subproblems, so it's n over s subproblems, n over s cubed, because that's how many like submatrix multiplies you have to do. And the cache misses to bring in each one is s squared divided by root b, or divided by b, sorry, because you just need to bring the matrices into cache, which just is over b. And we have here that s is root m, so you plug in root m for there, and so this is like m to the power 3 over 2, this is m, and then so you have m3 over 2 in the denominator, m in the top, so then that's why root m is then there. Does that answer your question? Great, thank you. Okay, so yeah, so one problem that I asked last time is like, well, this is great if you can choose s equal to this, but sometimes you may not know the cache parameters, or you may have different levels of your cache hierarchy, and so the issue is like maybe you need to add many levels of nested loops to tune for all the levels of your cache hierarchy. And also it's not very portable, because if you move the machine and then the machine is not exactly the same, then this code may not work exactly as well. So the topic today, as you might guess, we're doing divide and conquer again. So we talked about this divide and conquer matrix multiply last time when we did parallel algorithms, like we did work span. And this is just how it works. Like you divide for simplicity, we're going to make them square. So you have like n by n matrices, and you divide them into quadrants. So C is A times B, and then you basically do like matrix multiply on the quadrants, like horizontal, vertical, and so on. Like this A11, B11 is like this way, and then that way. A21, wait, yeah, A11, B12 is like that way, like the rows on the columns. Okay. So you can express your high-level matrix multiply as 8 submatrix multiplies with a matrix addition. And last time we were doing like the work span analysis for this. Yeah, and this is the same code as we had last time, but now it's just on one thread. And even still, in one thread, you still want to coarsen the base case because you're doing recursive function call overhead. So you don't want to do function call on dataset size of 1. So right now this is n equals 1, but actually in reality this would be a larger constant. And these are like the dimensions. So these are just telling you the corners up here, like the left upper right corner, or the left upper left corner for each of these quadrants. And then once you have the quadrants, because we assume that all matrices are the same size n, you just call this recursive multiplication using the corners. And then now the problem size is divided by 2. And yeah, that is it. Does this, people remember how this works? Okay, cool. Okay, so last time we said that the work was equal to the same as with the 3 loops. This is theta n cubed because we have this recurrence, 8 work n over 2 plus theta 1. And then by master theorem, this is n cubed. And we want to, another way to think about the work is, I guess underlying the master theorem is analysis of this recursion tree. So you start at the top with the work, and then you have 8-way branching, and each subproblem is a size n over 2. And so on like that. There's only theta 1 work at each level to split the subproblems, and then you get subproblem size n over 4. And then all the way down until you get to theta 1. And then this is like this is how the master theorem is. You have the number of leaves, which is much bigger than the thing that was f of n. This is n cubed. So the work is all concentrated in the leaves. And the reason that I bring this up is, even though you can directly apply the master theorem, is because you use the recursion tree more directly when you analyze cache-oblivious recursive algorithms. Okay, so we're going to bring up this. So like I said, we're going to analyze this recurrence. So this is the cache matrix Q of n. And there's two cases. One is if your submatrix fits in the cache, so this is sub n squared, which is the submatrix size, is less than Cm, where C is some constant less than at most 1, then you just incur n squared over b to bring in the submatrix into the cache. That is what we just had in the tiling. Like that's the base case in the tiling as well. And then higher level recurrence is the same, 8 n over 2 plus theta 1. So previously in the work, the base case was just theta 1 for n equals to 1 from an analysis standpoint. But now the difference is that the base case is higher up. M is the cache size. Yeah, the memory is unbounded size. The question. Exactly. And does it make sense why this is n squared over b? Of course. Yeah, C is just some constant at most 1 because you need to technically fit like 3 of these submatrices. Like you need A, B, and C to fit. And maybe there's a little bit of extra stuff like the metadata. So it can't be exactly M because then only A, B, or C could fit. So that's why it's like, you can think of C as like at most a third-ish because you need to fit 3 submatrices to do, like you need to do, C is A, like A times B.
If that makes sense. Now I'm just wondering why this is.
Yeah, it's like, I think from a theoretical point, it's like n squared is theta m, and then they're not so strict with the definition of, yeah, you could say like n squared is theta m, and then from a theoretical standpoint, it works out. But yeah, from an exact standpoint, like less than 1/3 is fine. Yeah, any questions on this recurrence? Okay, so yeah, so we're going to do the same recursion tree as we had before, or a similar one, but now we start at the top with Q of n. And we do the same splitting, like 8 Q of n over 2. This is the same 8-way splitting that we had for the work, and so on, like 8 again, and then Q of n over 4, and then all the way down. But however, the difference now, this used to be theta 1 for the work, and now this is theta Cm over b, because the base case is when n squared is theta m, and so n squared over b, if you plug in m, that would be Cm over b, which in the theta, the C just drops out, and that's m over b. So yeah, so this is the difference. The base case is now m over b, and the number of leaves that we have is also different, because we cut, in some sense, the recursion tree is now shorter, in a sense. We don't stop at 1, we stop at log 1/2 log Cm, because the side length, because the parameter n is actually like the side length. So now the number of leaves is, you still have 8-way branching, but the height of this tree is log n minus 1/2 log Cm, which is the same as like log of root m. And then, so the number of leaves is now less in this analysis. This is just an analysis thing. Like in the code is exactly the same. You can still think of it as recursion down to base case 1. But from an analysis standpoint, now the height of this analysis tree is shorter, and the number of leaves used to be n cubed, but now it's n cubed divided by m to the 3 over 2. And that is how, yeah, and that's just from this. Yes, yeah. So the base case is once it fits into the cache, you don't incur any more cache misses to bring more data in, because all the subproblems that you're doing are just subproblems on the thing that you have already brought in. Yeah, thank you. Yeah, so this is the number of leaves, and we're just going to do the same analysis basically that we were doing before. You take the number of leaves and you multiply it by the cache misses per leaf. So this is similar to what we're doing in the tiling. You have number of leaves, this is n cubed divided by m to the 3 halves times m over b, and then once you do the analysis in theta, that's n cubed b m to the 1/2. And if you remember, this is the same bound that we got in tiling. So the analysis doesn't really look hard, but I think it's a nice idea because in Cache-Oblivious algorithms, like this is just divide and conquer. You don't need to do explicit tuning for the cache parameter. Okay. And so for efficient Cache-Oblivious algorithms, like I said, there's no parameters, there's no tuning parameters, there's no explicit knowledge of the cache size. So there's a bit of a disconnect where the algorithm doesn't tune for the cache size, but you can see that we still did the analysis in the cache model. So the bounds are still in terms of m and b, even though they don't show up in the code. And yeah, and you can apply this analysis to any level of the cache. So in some sense, you are tiling automatically for all the levels of the cache. And it turns out that this is better in multi-programmed environments when the cache size changes over time, or the effective cache that you have changes over time. So efficient Cache-Oblivious algorithms, you can achieve the lower bound without explicit knowledge of DNM. There's a difference between the actual algorithm and the analysis of the algorithm. And so if you remember, going back to here, there's no block size, there's no memory size in this code. But if you write the tiling code, you had to set s as the parameter, and their s had to be related to m to achieve the bounds. But here, there's no parameter relating to the memory size. But we still analyzed it in terms of BNM. So ideally, Cache-Oblivious algorithms, the actual algorithm description, I think they're always recursive pretty much, or at least the efficient ones are. So they always basically do divide and conquer, and you make some argument about exactly like this. You make some argument about once you reach the analysis base case, what's the relationship between that and the cache size.
So you're not improving the algorithm.
We're not improving the algorithm? What do you mean? This achieves the same bound as the tiling algorithm if you could know root m in the tiling. Oh, no, that's for, here is n equals to 1. That's just a practical thing. You would set the base case. You don't set the base case equal to root m. You set the base case to just a large enough constant to amortize against the function call overhead. That's a practical thing. But for the analysis, you can assume that the algorithm recurses down to 1, because the base case would be theta 1. And that's what we did for the work, is that we assumed that the thing just recursed down to theta 1. Here, the actual algorithm is recursing down to theta 1, but the analysis stops at root m, because once you get past there, the entire thing fits in the cache, even though you keep dividing this up problems. Does that make sense?
Like I thought last time, but it's the cache for the naive, which is supposed to be higher.
Last time there were 3 cases for the cache misses, and it depends. It's relating the matrix size to the cache size. In the worst case, if the matrix is very large, then you basically get n cubed cache misses, because nothing will fit in the cache, and by the time you come back around, it's all gone. But however, here we are getting a factor of b in the bottom and also root m. Yeah.
But
So.
But there's a thing that applies to also very large builds, just that.
Yes. Yeah. Exactly. This applies to any setting of n. I guess if n is sufficiently small, this would just become n squared over b, if the whole thing fits in the cache initially. But for n sufficiently large, this bound would apply.
How large would n have to be doing this dividing? That would be faster than regular, just basic matrix multiply without the recursion overhead.
Just the loops?
Yeah.
I would say for any reasonable size, maybe 100 by 100 is not worth it, but once you fall out of L2, it's probably worth it. Maybe 1,000 by 1,000 or a couple thousand by 1,000. Yes.
And how did you go from the first line there to the second line?
This one? Yeah. So log n and this thing, you can divide. Is that how that works? Okay, so this is log root m. And then this is 8 is 2 to the 3. And so like this is 2 to the 3 parens, this entire thing. And then the log, you can switch the logs when the logs match. So like if you have log base 2, then you can switch out this LG in the base. And that's how you get this. Make sense? Yeah, so LG is log base 2. Yeah, and then if you turn this into a log base 2, then you can swap out the exponent. Good. Good. Questions? Okay. So we're just going to do a few more. Oh, yes, please.
Analysis, like the
Go back.
program does not have any cache specific information and it cannot be tuned also. It's just that the analysis can be done on the basis of.
Exactly. Yes, exactly. Good. Yeah, the code does not have any cache parameters. Like it does not in the tiling version you had to set S like as the subproblem size. And that to achieve the bounds has to be related to the memory size.
Yeah, but say we know the M and B here.
Mhm.
Say we know it, but we can't still modify the code we've written to yeah, there are no
Yeah, like if you knew even if you knew M and B,
there's nothing
this
you
is
can do.
there's nothing you can do here. You're just cutting in half. Yeah. From a practical standpoint, if you do know M and B, like the theory is exactly the same in the theta. If you do know the M and B, an efficient like tuned tiled implementation can be faster than a Cache-Oblivious one, which kind of makes sense because like this is like if you had exact knowledge, like obviously this is like it's leaving constant factors on the table in some sense, like you're just cutting in half. But this is better, like for example, if you don't know the cache size, or it's also more portable if you change your machine and now you have to retune the cache size, which may or may not be something that you want to do. And it's also good, like even if you run on one machine and if you have multiple jobs running at the same time and they share the memory, then your effective share of the memory changes over time. And so this divide and conquer thing would be better for your effective changes in memory over time. So it depends on your use case. Like if you did exactly know M and B, you may, and you are guaranteed to have a quiet environment, you may prefer the tiled implementation. But if you have these other constraints, like maybe you don't know M and B or M and B is changing, like on different platforms, then you may prefer divide and conquer.
What's the scope of how much of this that we're supposed to know for a test, for example? Like, would we have to know how to draw that recursion graph and analyze that? Or is it just
Yeah, you would have to know how to do this recursion tree. This is basically this is the common way to analyze Cache-Oblivious algorithms, or recursive algorithms in this caching model is finding the height, finding the cache misses per leaf, and finding the number of leaves from the height, and then just multiplying them.
what a leaf is
Yes, exactly. Yeah, so the base case tells you that n squared is theta cm, or theta m, I guess, because c is a constant. Okay. So let's move on. We're just going to do more Cache-Oblivious algorithms. We're going to move on to a new problem, which is called heat diffusion simulation. And this is so we're changing problems. This is the 2D heat equation. And basically the way it works is that you have a grid and it has points x and y, like in space, and it has time. So if you think of it as like the initial spatial grid is 2D, and then over time you have a third dimension, and you have this function utxy, which is the temperature at time t on every point on a point xy, and you want to write some code to find this equation or to solve this equation. And in math, you can take derivatives, and we want to write some efficient code to solve or to simulate this kind of thing. So at the beginning of time, you start with one hot point, and then over time, like the other areas become hot and they become less hot depending on their distance. Like the areas farther away are less hot than the areas closer to the source. And you have some just alpha, which is this constant for diffusion. Yeah. Yeah, so for simplicity, we can start with it in one dimension. It's easier. So in one dimension, we just have a vector, and let's just say that the source is on the left side, and yellow means hotter, and blue means colder. So, and then closer to yellow, like red, is warmer than blue. So it's just going that way. And so we take the derivative, du over partial t, and this is for one dimension, but you could do the same thing for multiple dimensions. This is complicated. You don't have to know like this level of calculus on the exam. If you do know this calculus, it's great. But if you don't need to know it for the exam. The only thing to note here is you basically this is for one dimension. So yes, for one dimension. So taking partial with respect to t, and you basically do this approximation that you do t plus delta t and minus tx, and then you divide by delta t. And as delta t gets close to 0, then that approximates the real thing. And then there's some basic calculus that we don't have to understand for this exam. But basically, what it comes out to is you want to approximate this. This thing, which is an approximation for the derivative, and then you get to some function. Like this is alpha, which is a constant, and you get it to u t x plus delta x minus 2 times u tx plus u t x minus delta x. The whole thing divided by delta x squared. And the reason that this is interesting for us is that we are trying to approximate this with some discrete quantities that we can compute in code. And another interesting thing is that you can see that if you are interested in the result at time t, you just need to have the values within some x, like minus delta x plus delta x. Okay? So how do we write this in code? And the high-level paradigm for this type of program is called the stencil computation, which is a very common paradigm in high-performance computing and in parallel computing. And so this is the equation that we had before, exactly the same. And the stencil computation, basically you have a grid, and you update every point in the next time with a fixed pattern of updates from the data in the previous time. So if you represent this as a grid, we have one dimension of x, and we have the dimension t, which is growing up. Then every point in the next time is related to the points in the previous time in some way. And for simplicity, if we set delta t equals to 1 and delta x equal to 1, then when you actually write it in the code, this is your grid. The time, the value at t plus 1 for x is the value at the previous time t for x plus alpha times this thing, which is related to this equation that we just derived, t x plus 1, tx minus 1. So it's like in the next time, you want to find tx, like here, and you need these 3 points. T plus 1x, tx plus 1, tx minus 1. Okay, yeah, so this is exactly what I just said. Every new point in the next row is related to 3 previous points in the previous row. And you want to compute them all, because you're trying to do the entire vector's diffusion over time. So like this one is related to these 3 points, and then the same pattern applies to every point in this row. Every point is related to like this triangle underneath it. And you can see that the boundary, like these yellow points, are never going to get updated because they don't have a third one to the left or to the right on the other side. Yeah, so yes, yeah, and then you just can keep reusing them as you go up. But these are all changing at every time step. And on one thread, you just imagine like you make a loop and you go through, like you start, these are some initial value. And when you initialize your loop, you're computing this next row. You just loop over these points and you compute like the next function based on these three, based on this equation. Questions on this? Oh, oops. Yeah, and then once you have computed this row, then you want to compute the next row because you're trying to do this entire thing over time. So you're just computing this next row here as a function of now these points that you've just computed in the previous step. And again, like these are the same, and then so on and so on through the entire times.
Why does the delta x
We happen to set delta x to 1, and so dividing by delta x, divided like 1 squared is 1, and so you divide the whole thing by 1, and that goes away. But x plus 1, x minus 1 is the delta x here. For just to make it really easy, we set it to 1, but for more fine-grained simulation, you can set t and x smaller than 1. And then like the points would just become closer, and the times would become closer. But for illustration, 1 happens to be a very easy example. Questions? So since we're talking about caching, how would this code perform with respect to caching? Just doing this loop version. Every iteration just needs to do like the row.
Then it will be swapped out. The next two rows for or the next row for the next. Every time it is next one. Assuming the entire row at least fits in the cache, you will need to swap out one row and the other.
Yes, so you're saying like, so we can't do tiling. Yeah, you can't do tiling. You can't do rectangular tiling because, like, if you cut a rectangle, then you're missing some of the dependencies. So that subproblem cutting is not going to work. But if you just do the loops, think about like, so we're just computing this column or this row here, like, so we're reading it horizontally, which is good in some ways because we take advantage of the cache line. But what happens like when when you finish this row, you're going to come back around here. And now you need these points. Dx over b. What is yes. T is the height. Yes, exactly, because you have to compute this entire matrix, which is volume Tx, and you just get the cache line, the horizontal benefit. Does that make sense to everyone? Yes. Yes, exactly. We're going to get to that in a moment. Good point. Yes. So the very initial version of this is you can just keep around the entire thing, and that has volume xt, and of course it costs xt work to compute the entire thing. And yeah, so like we were just saying, you have to, in the naive looping version, you compute the row first, and then you come back around to compute this one. And if this row does not fit in the cache, this stuff is gone by the time you come back around. And so you just get the factor of b because you get the cache line benefit. However, there is some potential for reuse because you can potentially do better because these, like you have dependency on these things. So ideally, you would like to have these things around still. And you already said this. If you only care about computing the next row, computing the next time step, you need to keep around the entire matrix. And how many rows do we need? And you just said 2, which is exactly the case. You just need to keep the previous row and the next row, and you just keep flipping them. Does that make sense to everyone? Okay, great. Yeah, so you can keep rows, just two. Okay. We're just gonna skip directly to the Cache-Oblivious version. There is a tiling version. You don't cut rectangles, you cut like diagonals, basically. But if we're talking about Cache-Oblivious algorithms, we're gonna skip to this one. Question so far? So this is the code to implement this cache, to implement this stencil. It's very easy. You you get two rows of size n each, where n is your horizontal length, and this is just the computation that you have to do. And you loop over time, and then you loop over space. So you're doing one row at a time, and then you just go through the row in this double loop. And x is the fast-moving dimension, which is the horizontal dimension. And then this is called the even-odd trick. So you switch which one is next and previous, depending on where you are in the parity. And for every time step, or for the next time step, you are just computing, yeah. So this is time step plus 1 mod 2. So like depending on if you're even or odd, you are either row 1 or 2, and then you just compute the kernel into the other row. And the kernel is just the equation that we said before. Since it's in 1D, minus 1, 0, and 1, and you index it by, this is like pointers, like u and then x. Does this make sense to everyone? Oh, yes, the even odd is just because you have two rows, we're not keeping around the entire matrix. So once you compute what is, in the first one, like once you compute what is previous, then you compute what is next into the other row. But in the next round, what was next in the previous round is becoming previous in the next round. So you just switch off which row is which, and you can do that with like the even, with like if you're even, then you are currently in this row. If you're odd, then you're currently in the other one. And then that tells you which one is next and which one is previous. Good question. And exactly, people said, how many cache misses are there as a function of n and t? N is the horizontal length. Assuming LRU, if n is bigger than the cache size, then the cache misses are nt, which is the volume, divided by b. Great. Yeah, it turns out that you can do better. So the way to do this cache-obliviously is, as you might imagine, to do a recursive divide and conquer. And the way it works is that, as we said, like you can't cut rectangles because then you don't get the dependencies in your subproblem. So here we're going to cut trapezoids because trapezoids have diagonal slope on both sides. And here, when you, in this example trapezoid, like say this is the subproblem that you need to compute, all your dependencies are within this trapezoid, like here, here, and so on. And the way that you can guarantee that is that you need to cut the slope equivalent to the x dimension in your stencil, or the x change in your stencil. So here, like delta x was 1, so it made it really easy. You cut the slope equal to 1. But depending on the number of dependencies you have, the slope may not be equal to 1, -1, or 0. So we're going to recursively cut the entire 2D space into these trapezoids. And then those subproblems are going to, like the high level way this is going to work is you have this 2D grid that you're trying to compute. You're going to recursively cut the subproblem, and then such that when you start at like the lower left corner, and you're just moving up. And those subproblems are going to be recursive divide and conquer, so they're going to at some point fit in the cache. And the analysis will look this similar like we did for the matrix multiply. Yeah, I already answered this question. Why are we not doing quadrants like when we did Tableau when we were talking about work span? And we can't do quadrants because then you don't get the dependencies right. Okay. So yeah, so there's two cases for the divide and conquer because now this is not necessarily a square. One is that if the width is at least twice the height, so that means the trapezoid is wide, we're going to cut it horizontally. So if the width is more, or at least twice the height, you cut the trapezoid with a line slope -1 through the center like this. And then you're going to get these two sides of the subproblem. first you have to compute the one on the left, and then you have to compute the one on the right, because all the dependencies are satisfied in this one for the points, but here you can see like this point has some dependency in there. So this needs to be finished before you compute this. Yeah, and it's diagonal and not vertical because of the way that the 3-point stencil works, like the dependencies. Can you swap the order? No, because you depend on the stuff in the left. The other case is when the trapezoid is tall rather than short. And here you just cut it straight through the middle. That one is easier. You still need to do the bottom first because like this point has dependencies here. So this row needs to be computed before you start computing this row. And so that means you need to compute the bottom first before you compute the top part. So yeah, and this is just saying if the width is less than twice the height. So the way that you're doing these cuttings, the width and the height are always going to be within a constant factor of each other once you get to the base case, which is important for doing the cache analysis. Okay, so the very base case, once you stop this recursion, is just the height equals to 1. So once you have height equals to 1, you can compute just all the next points using the bottom row that you have. And you can do these points up above in this row, you can do them in any order because you have all of these and they don't depend on each other, they just depend on the previous row. And this is the C implementation. Oh, sorry, yes. Go back.
When we are cutting the entire space trapezoid, what about the remaining points?
Can you say it again?
Like, we're not covering all of the points in the square, the rectangle.
Mhm.
If you're cutting the space trapezoid.
Yeah, because you can ignore the boundary points.
So you ignore every other points outside of the. We've cut the space into one big trapezoid which we want to do divide and conquer.
Mhm.
But we're always doing divide and conquer within for all the points in the trapezoid. So we don't care about the ones outside. Shall we not computing?
Can you say it again?
Like, could you go back to the
go back.
Yeah.
Like this one?
Yeah, I mean if this is your trapezoid, then we will not compute the points outside.
No, this is one subproblem. In the end, we will compute all the points. So we start with it. Initially, we had an n by t grid, and we're just recursively cutting that grid into trapezoids.
Yeah, but say you have a huge set of writing grids. So ideally, what you want to do is all of the points you care about, you want to fit them into one trapezoid. Right?
I mean, ideally, you're trying to compute like the ones at the top in the n by t grid. Like, because we're keeping just 2 rows, you're throwing away like all the bottom points, but you still need to compute them because when you compute all the rows, like every row depends on the previous row, so you still need to compute the rows even though you're not going to keep them around. And so you need to compute all the points in this grid to get the last row. It's like dynamic programming in a sense, like you just care about the end, but you need to compute the entire grid.
Like I think what he's trying to say is there might be overlapping your subproblems, like your trapezoid will not cover every single trapezoid will not cover all the points. So if this subproblem has solved the points related to this trapezoid, and I create another subproblem that has an overlap with this particular trapezoid, in that case, how do you actually do that?
Where would you get a case where they overlap?
For example, let's say now this trapezoid has not covered all the points, right? And
Yes.
there might be some points in the huge matrix that are not covered in any of the problems. Like
There are no
trapezoid
such.
does not exactly make a perfect rectangle, right?
Well, the initial trapezoid is just the initial trapezoid is the entire rectangle. We can look at the code maybe, and that may become a little bit. We can go through the code and then maybe see if that answers. Yes, but we are with this decomposition, we are not missing points in the grid. Okay. So let's look at the code. So it has these parameters: t0, t1, x0, dx0, x1, dx1, and t0, t1 are like the height, like times 0 times 1. x0, dx0 are like the leftmost point and the slope on the left side, and x1 is the point on the right side and the slope on the right side. Okay, so the height is t1 minus t0, and the base case, like we said, is when the height is equal to 1. And when the height is equal to 1, we just do the same, just like the inner loop that we had before. Like now we're not, before we had two loops, 1 over time, 1 over space. Now this is just over the space that we have in the subproblem. Okay. And the most important part is in this recursive decomposition. So if the height is greater than 1, then we have these two cases. One is like diagonal cut, one is horizontal cut. This is saying if 2 times the width plus this dx1, these are the slopes, times the height is greater than 4 times the height, then you're picking the midpoint of the trapezoid, and then you cut the trapezoid. Yeah, the height is the same, t0, t1, but now the slope on the left side is, the slope on the left side is unchanged. This is the left subproblem. Now the right point of the subproblem is the midpoint, and the slope on the right side is -1. And now you have to do this one first. Like we said, you have to do the left subproblem first and then the right one. And then the height is the same. You pick the midpoint as the left point in your right subproblem. Slope is -1 on the right side, or slope is -1 on the left side, sorry. And x1 dx1 is unchanged. So this is how you do the space cut. You do like a -1 cut in the middle, or a line with -1 slope in the middle. And then the time cut is easier. You just cut the height in half, and you just, these parts are unchanged. You set the height now. This used to be t1. It's t0 plus half. These are unchanged. x0. These are all unchanged from the initial call. Now the second one, the top one, is bottom plus half, plus half. Initial height. This is the new x. This is how much the slope went up. Like slope times y distance is how many your x points have changed. So this is why this is x0 plus how many x points you have moved over. The slope is unchanged, dx0, and then same for the x1. This is how much your right slope has changed based on how much height you went up plus dx1, and dx1 is unchanged, which is the right slope.
How would this work if you had a really, really tall grid that was maybe like 10 tall by 3 wide?
If you had a really tall grid, you would just keep making space cut or time cuts. Like you would just keep cutting it from the horizontal part, because based on these conditions, like this is saying if the width is big enough, then you cut it in the width dimension. Otherwise, you cut it in the time dimension, which is horizontal. And in the initial grid, which is 2D, like the rectangle, slope can be 0. So that's how you get the vertical part in the beginning. So 4 times LT is 4 times the height. And this x1 minus x0 is like the base of your trapezoid. And 2 times the base of your trapezoid plus LT is like the height. And this d1, dx1 minus dx0 is slope on the right side minus slope on the left side. And yeah, so if you multiply that by the height, I guess this could also become just probably like I think this might be possible to do it in the, just based on the bottom part, like just based on x1 minus x0, which is the bottom length of your trapezoid. You can think of this as if your trapezoid has some base and it has some height, and this is just trying to make a relationship between the base and the height, like saying the relative size. Um, yeah, and this is just cutting some midpoint.
On previous slides, you were saying you do a horizontal cut in some cases.
The horizontal cut is this bottom one because this is LT is the height, and then this is cutting the height in half, and then you're just setting this is the bottom, T0, like the base. This is T0 plus half the height. Now the top, this is the top half subproblem. This is T0 plus half the height, and then going up to T1, which is your initial top height. And then the reason that these x's have changed, because this is the top half of the problem, so you need to compute the new base.
And so which cases? Again, when it was wider or
This is when it was tall. This is when it's tall, and this is when it's wide.
In the base case, why are we only using previous values from x and not like x minus 1?
Sorry, could you say it again?
So in the base case, we're updating.
Oh, because kernel is like a subfunction that calls x minus 1 x sub. Yeah.
And then I had another question. So in this case, when we're working with trapezoids, we still have dependencies.
Yes. So that's why these subproblems are in serial.
So why is it okay for us to use trapezoids and not dependencies?
Why is it okay? Because eventually you want to parallelize this.
But we still have dependencies.
So we're going to cut the trapezoids in a more fine-grained way momentarily. But no matter how fine-grained you cut the rectangles, you always have dependencies between them.
But won't we still have dependencies between the trapezoids?
So right now, the simple case is that you cut one trapezoid per cut. To parallelize, you're going to cut more than one trapezoid per cut. And then we're going to show how that can satisfy some parallel dependencies. But if you cut it into rectangles, no matter how many rectangles you cut in each recursive call, you will always have dependencies between the rectangles. We'll get there briefly, and then we can stop after that to see if there are still questions. Any questions on this? Okay, so since we're talking about caching, we can do cache analysis. And the same, we're just going to do this recursion tree, pretty much. And this recursion tree is even easier than the previous ones that we had, because now we're doing two-way splitting. And the base case is just these trapezoids. So the bottom case is the same as we always have, when the bottom of this leaf trapezoid just fits in the cache. So the cache misses are theta m, or the width is theta m, sorry, because once remember, like, we're doing this even odd thing. So once this base of the trapezoid fits in the cache, you can fit the entire, you're just using the same memory to compute the entire trapezoid. So now the entire thing will fit in the cache. And the leaf trapezoid has theta hw, and because of the way that we did the splitting, h is theta w. So now this is theta w squared points that we're computing. And theta w squared work, because the work is equal to the points. And since w is less bounded above by m, each leaf incurs w over b cache misses, because you just have to incur the misses to bring this entire bottom part into the cache. And so yeah, so this is like the same type of argumentation we were doing before. How many misses does it take per leaf? And then how many leaves are there? So the number of misses per leaf is w over b, where w is the width. And how many leaves are there? Well, we started with nt, which is the volume of the entire rectangle, and we divide by hw, which is the number, like the size of each trapezoid. And so there are nt divided by w squared leaves, and the internal nodes, but the internal nodes don't really contribute much because there's theta 1 each. You just have to do splitting. So total work is nt divided by w squared times, this is the number of subproblems, which is nt divided by w squared. And work per subproblem is w squared, so the work is the same, theta nt. And cache misses is number of leaves times misses per leaf. So that is number of leaves, nt divided by w squared, cache misses per leaf, w times b, and then so that gives you nt divided by BW. And then since W was set to M, so this is NT divided by BM, which is a factor of M better than what we had previously. Previously, we just had B in the denominator when we did the looping. Now we get an extra factor of M in the base. Exactly. Because of the splitting, at the end, once we get to the base case, H is theta W, and vice versa. So that HW is then theta W squared.
How do you know there are NT over HW?
Good. So there are, the total volume of the grid is NT, and then this is just the number of leaves is how many subproblems there are. And since this is covering the entire grid, the number of subproblems is just the total size of the grid divided by the subproblem volume, which is HW. And because of the way that we did this decomposition, that is W squared at the base, where W is like M.
Since only the leaves really contribute much to the overall thing, why are you multiplying the total leaves and internal nodes by W squared?
This is the number of theta NT times W squared is the number of leaves and internal nodes, and the number of internal nodes is asymptotically small compared to the leaves. Yeah, because you're doing binary splitting. Good, very good. Yeah, and to complete this is one dimension that we did it in, but for arbitrary dimensions, the M decreases in the exponent as with 1 over D, where D is the dimension. This is still okay for 2 dimensions. This would be root M, but for higher dimensions, the story is a little more sad because this drops quickly with D.
So why is a leaf W over D Cache-Oblivious is not our size of the
Good, because we're doing this even odd thing, and so you overwrite. So the actual space that you're using is theta to store this trapezoid. If the base is W, the entire memory that you actually use to compute this is theta W. Yeah, does that make sense? Yeah, that is subtle and a good point, because if you actually computed this entire volume, that would be W squared ish, W squared over B. Exactly, yes. So once you can fit the base of the trapezoid into the cache, then you can compute the entire W squared points. And yeah, so like I was saying, like we decompose the entire rectangle, so you can end up with trapezoid like this, where the side is a vertical line. Good. Questions on this? Okay, great. So yeah, so this is just a picture of what the trapezoid algorithm looks like. This is a simulation. So N was 95, T is 87. This is a software simulation with an LRU cache. And so the purple is cache misses, and the green is cache hits. So looping code would just be like this. And if N is bigger than the memory size, then you just incur cache miss every B points. However, you can see in the trapezoid one that there's much less cache misses over time. And like you can see that like this is growing from the bottom up. This is kind of going like up this way. So the axis pattern is actually quite different.
So in the previous slide, when you were calculating the number of leaves, was that assuming that we don't have overlapping subproblems, though we do have overlapping points in other trapezoids?
Is that assuming that we don't have overlapping subproblems? I guess in a sense, like maybe if you count the boundaries as overlapping, like they have, it's not really overlapping because you never compute the same point twice, but there are dependencies in other trapezoids. Yeah. You don't recompute, yeah, so within each trapezoid, like they are partitioned so that you never repeat any like 3-point dependency, but the dependency may lie in a different trapezoid. Make sense? Um, yeah. So empirically, they ran this. I didn't run it, but there were some experiments. And then when they actually did this experiment, they found these following numbers. For the Limpy code, it does about 1,560 iterations per second. Trapezoid version does 1,830 iterations per second. So this is a bit not exactly what we saw in the theory, because for 1D, we saw that it would be like M in the bottom, and M is usually pretty big. So what are some reasons that they might be so close together? Sorry, this is a question. Yeah, that might be one of the reasons. Recursion overhead is probably not responsible for the entire difference, because you can see, for example, in matrix multiply, you could see that the recursive version is much faster than the looping version, but contributes.
Is it continuous memory? Like,
Mhm.
because you generally prefer continuous memory in order to access faster.
Mhm.
I think hardness, you are accessing it.
Yes, exactly. So what I guess the main point that I wanted to make is exactly as you said, like your hardware is designed to accept continuous memory accesses. For example, like you get hardware prefetching, which is when you ask for one cache line, actually like the thing will load multiple cache lines for latency hiding. And so actually like the cache misses in the model are maybe not exactly all equal cost, despite what we said in the model, because the model is discounting cache misses for simplicity. There are more advanced models where basically they include like a small parameter. So rather than in the initial cache models, like every cache miss counts the same. But in follow-up cache models, the first cache miss counts for 1, and then the subsequent ones count for alpha much less than 1 if you access them sequentially. So using more refined models, you can try to capture the more realistic performance. And another issue is when you run it on one thread, you can't saturate the memory bandwidth because you just one, you don't process fast enough to do it. And so, yeah. So now we're going to talk a little bit about parallelism, like I promised. Yeah, so at a high level, if you minimize cache misses in the serial projection, and the serial projection is just, if you write a program with the parallel constructs like spawn and sync and for, you just remove the parallel constructs, you get a serial program, and the serial program should still be right, ideally. I mean, if the parallel version was right, this projection is definitely right. And if you minimize the serial cache misses, then you should minimize the parallel cache misses as well, because you will only get at least more cache misses in the parallel version than in the serial version. Because like maybe the scheduler may move some stuff around, and then that's how you get more, but you cannot get less. So yeah, okay. So we're going to try to parallelize this trapezoidal decomposition. You cannot parallelize this horizontal cut because you need to compute this row before you start computing above. So that is not going to work. But maybe we can parallelize the space cut if we do a more fancier thing. So this initial cut also is not going to parallelize because you need to do the left side before you do the right side. However, this is where we're getting, like I promised before, if you cut slightly smarter way, so rather than cutting into 2, you can cut into 3. So this is your initial trapezoid, this big thing, and now you cut kind of like a triangle in the middle like this, and then you have 2 trapezoids left and right, and you have a triangle here. Now these 2 trapezoids are independent, and then you can compute those in parallel, and now once you have computed both, 2 has dependencies in both, but you have computed them, so you're good, you can do 2 now. And this is called a parallel space cut. So rather than cutting 1 line, you cut 2 lines. And that's how you do this parallel decomposition. Make sense? And then another way, like if your trapezoid is upside down, you just cut it upside down. But the idea is the same. I guess slightly different is now, before, like the 2 trapezoids could be done in parallel first, and then the triangle had to be done next. Now the triangle has to be done first, and then the 2 trapezoids can be done next. Those can happen in parallel. But it's a similar idea. and showing some numbers, doing this 3000 by 3000 grid for t is at 1000. So this would be, yeah, this is in 2D. The parallel looping, like you have to do the rows in parallel, or sorry, you have to do the rows serially in the looping version, but you can do all the points in every row in parallel. So that's where the parallelism comes from. And they get, so doing this very simple parallelization method, you can get about 2x speed up. This is on like, yeah, this is on 4 cores. Get 2x speed up here. However, using this parallel decomposition, you can get 4x speed up here. And the difference, the reason why this is farther than we saw in the previous number, like this is about factor of 2 in the serial version, is because the input is bigger. And so the benefit was not as much when it was on 1 core, but still a factor of 2 is not what we were promised when we had a factor of m in the bottom. Yeah, so, and another take-home story from here is the parallelism, like achievable parallelism from a workspan point of view is much higher in this. It's very easy, like you just parallelize the entire row. But however, like this, there are more dependencies in this. So the actual theoretical parallelism is less, but the achieved speed up is more because it uses the cache more efficiently. So yeah, so one important thing to remember is from a practical standpoint, even if your theoretical parallelism is better, you may be blocked by the memory in terms of speed up, not necessarily by the actual amount of parallelism you have in the algorithm. Okay. Yeah, so like I said, the memory bandwidth may be the bottleneck rather than the actual parallelism. There are several issues when you're trying to get realistic speedup. The first one is insufficient parallelism, which you can diagnose by doing the workspan analysis. Another one is the scheduling overhead due to the parallel scheduler. Usually, if you have done enough coarsening for your work chunks, this should be fine if your algorithm has low span. Another one is lack of memory bandwidth. A really easy way to diagnose this is with the caveat that, so you have one, like if you have a serial program that uses some amount of memory, you can run p identical copies of it at the same time. If you have enough memory to hold the p copies, of course. And if it runs slower, then you are memory bound. Does that make sense? Like if you get less than p speed up. You can also diagnose this by removing physical memory and then running it. And if it got slower, then, but that's like a more heavy-handed way to do it. This is like a software way to do it. And last one, which is really hard to diagnose, is contention. So contention is like if you have locks and multiple threads are trying to get those locks at the same time. And there are some tools to detect like when you actually run the program to see how much contention you got, but it's very hard to tell like theoretically how much contention you might get. So that is harder than the rest of them. One way to fix false sharing, which is also like a kind of low budget way to do it, is you just add more padding between the elements. So like one really common thing that you might do is like you want to keep partial sums, for example, or partial accumulations, and you have like p of them, like one per thread. And if you put them all in a p-size vector, then that they're not going to get false sharing. So you make the vector like p times cache line size. It's not fancy, but it'll work. And I don't think I have time to get into this, so we can talk about this later. Thank you.